All right, this is going to be our first installment of organic chemistry and the functions. We will discuss on another video the prefixes used when naming your functional groups or your organic compounds at another time. But we first need to be able to identify what we are working with. So there are three basic organic and functional shapes. We have an alkane, an alkene, and an alkyne. Now there's a couple of things we need to know about these three items. Their names tell us what type of bond is happening. So you'll see here that I have them in this particular order, and that is not by chance. We have alkanes, alkenes, and alkynes. So we have 1, 2, 3. In this order, one of the things that we know about alkanes is that they are full of single bonds. So that is what we see here. The bonds between our carbons are singular in alkanes. In alkenes, we have a double bond, at least one, between our carbons. And then we have our alkyne, which is going to have at least one triple bond. Now, the characteristics of these are we are dealing with hydrocarbons. So everywhere you see a bond that does not have an element, in these particular cases, we are dealing with hydrogen. So we have hydrocarbons here. Our alkane is a saturated hydrocarbon, meaning that wherever carbon has an available bond that is not between another carbon, hydrogens are going to be there. Alkenes and alkynes are unsaturated hydrocarbons. So that means because one of my bonds for each of these carbons is taken up by a bond between the two of them, it is not saturated as much as it could be with hydrogens. And the same thing applies to alkynes. Now, in order to determine what we have, there's also a formula that goes with each of these particular functional groups. So, you see here, C with a subscript of N, H with a subscript of 2 times N plus 2. So this is letting me know that N is going to represent the number of carbons that I have in my structure. And for me to determine how many hydrogens I should have for an alkane, I would take 2, multiply that times the amount of carbons there are in the structure, and add 2. Okay, so if we were to do this one here, we have 2 carbons, so this would be C2. Then we would plug in 2 here, where we have 2N, so 2 times 2 is 4, plus our extra 2 gives us 6. So it's saying for a carbon containing, or hydrocarbon containing 2 carbons, for it to be an alkane, I should have 6 hydrogens. So let's count those bonds. 1, 2, 3, 4, 5, 6 hydrogens in that particular structure. So that works out. Let's take a look at alkene. It's telling us Cn, so C and our subscript of N is the amount of carbons that we have. Then we have 2 times N. So that's going to be 2 times the number of carbons. So we have 2 carbons. So it's telling us we're going to have C2 and H4. And if we count those bonds, we see 1, 2, 3, 4 hydrogens. And then if we take a look at alkynes, we have 2 carbons. So we have C2 again. Then we have H2 times 2, which again is going to be 4. But alkynes are going to be -2 because there's a bond taken from each of those carbons and it's bonding to the neighboring carbon. So here we would have 2 times 2 is 4, -2 leaves us 2. And here you can see there are 2 available spots for hydrogen. So those are going to be our basis of knowing the types of bonds or structure we have. Now we're going to discuss our functional groups. And there will be 8 that are discussed. We have alcohol, aldehyde, amide, amine, carboxylic acid, ketone, ester, and then ether. And I know you say these are words, we've seen these before. So what difference does it make in organic chemistry? Well, these functional groups will change the nature of our hydrocarbon and will help it to determine what it's doing. So when we look at strings or our condensed formulas for compounds, there are certain groups that might be attached to our hydrocarbons. So for instance, we have alcohol. Alcohol's functional group is an oxygen and a hydrogen, and they are going to appear side by side, just like that. And the ending for alcohol, to name alcohol, or the suffix is going to be OL. So one of the ways I remember that is the ending of alcohol is the same as the ending and the naming of those organic structures. Another what I call light bulb moment, I think about people going to the bar for the first time and they're oh so excited. So that's one of those kind of gimmies that there are. Then we come to one of the ones that I'm going to skip to because a lot of times people get very confused. So here we have a ketone. And if you look with an imaginative eye, that kind of looks like an old-timey kind of skeletal type key where the bottom is here and the handle is up top. But the reason I go ahead and I show this instead of just going straight to aldehyde is because when you're going down your parent or your strand of carbons and you notice something that is not a hydrogen, what I call an anomaly in that line, you're going to want to stop. Look to the left and look to the right and see what it is attached to. And in this case, you would see that this ketone is just going to be attached in the middle of a run. Each of these just lets us know that carbon is attaching to some other type of chemical structure. So with us knowing what a ketone is, I would like us to now go back to aldehyde and you'll see why. Aldehyde, you see, there is a ketone. But remember I said we must look to the left and to the right. So we're going down our hydrocarbon strand and we get to this carbon here. We have a double bonded oxygen. That is definitely something different because in all our other structures we were dealing with just hydrogens and carbons. So once we start seeing something different, we need to take a pause. So here we found something that looks like the ketone, but when I look to the left, there's nothing there. But when I look to the right, there's a hydrogen here. And one of the things I like to remind people, when you are dealing with aldehyde, it is a hydrogen hiding behind this ketone. Okay? And the ending, when you're naming your functional or your organic structures that contain an aldehyde, the end of that word will be changed to AL. Much like the word aldehyde, where that hydrogen is hiding, AL will be the suffix for that organic structure. And that will all come into play on our next installment. One thing I did neglect to mention, that when we're naming ketones or ketone-containing structures, the ending is going to be O-N-E, just like you see there in ketone. So the ending of those organic structures are going to be O-N-E. Okay? Now here we are, we see a amide and a amine. Okay? And when we think of these two, I want us to automatically think of nitrogen. AMI, AMI. You only have two structures in these 8 that contain nitrogen. So we're first going to start with amine. I like to tell everybody, think about carbon telling everyone that nitrogen is all mine. Or either the nitrogen is saying that carbon is all mine. Okay? But then let's take a look at amide. And this is one that's quite often mistaken for the other. Whenever we're naming things that contain oxygen, we typically change the end of oxygen to oxide, I-D-E. So if we think about the sense of how oxygen changes the naming, we're going from an amine to an amide. This amide is containing that oxygen to change that whole word from amine now to it being oxygenated, and it's an amide at this point. Okay? One of my next favorites, and before I move on to that, when we are naming our amines, your ending is actually going to be YL and the word amine. And we will discuss the naming of amide in the next installment. Now, with carboxylic acid, one of the things that I tend to think of when I see this word is boxcar. And when I think of boxcars, those have to do with trains. So when I look at the functional group for carboxylic acid, I have a ketone, but then when I look to the left, there was nothing there. But when I look to the right, there is an alcohol group. So I have a ketone and an alcohol, all of which contain the letters to spell the word chew. Much like our trains that contain boxcars, it is going to spell out chew, chew. Okay? Then we have ester and ether. Okay? To begin this one, we're going to look at ether. I like to tell everybody that central atom is going to be an oxygen instead of a carbon. And it's going to have a run on ether side. Okay? So just like the word either, there is a run on either side of that oxygen. And when we are naming these, our runs or our hydrocarbon runs that are attached to our ethers, we would use the appropriate prefix, and the ending for each of those groups would be YL. They would be placed in alphabetical order, and it would end with the word ether. And once again, we will be discussing that in the next installment of organic identification and naming. All right. Then we have ester. Ester is going to be an ether and a ketone. Ether has finally had somebody to reach out to. So I like to tell people, if you see two oxygens and it's not attached to a hydrogen, you've got an ester. Okay? Being able to identify what makes these functional groups different from one another is what's going to allow you to be able to point out what you are working with and what direction you need to go. So I hope this has been helpful. Please feel free, stop by your local Dollar Tree or Walmart, grab yourself some index cards, make the game play, name that functional group, describe that functional group, even flip them over and play memory, flipping them over and seeing if you can match what goes together, much like that childhood game with a deck of cards. Thank you and happy studying.